Welcome to this explainer. Really pumped you're tuning in for this one. Today, we're diving into something that is absolutely foundational to our modern world, the IC design flow. You know, it's honestly fascinating. It's that exact step-by-step journey of taking a mere, abstract idea and actually transforming it into a physical, microscopic silicon chip. It's basically the ultimate high-tech blueprinting process, and we're going to walk through the whole shebang from start to finish. Let's get right into it.
Okay, let's dive into this. Here's our 4-phase roadmap that's going to guide us through the entire 11-step IC design flow. 1. Idea to logical code. 2. Synthesis and floor planning. 3. Placement, clocks, and routing. And finally, 4. Final checks and tape-out.
Starting right off with Phase 1, Idea to Logical Code. This is where every physical chip begins its life as a conceptual blueprint and lines of code.
Let's actually look at this like a real-world, chronological project roadmap. These first 3 steps really kick off the whole project. Day 1 is all about specification. Then by week 1, we're deep into RTL design. And hitting week 2, we're already executing functional verification to make sure everything works.
All right, so step 1, specification. This is simply defining exactly what we want our chip to do. Nothing fancy yet. For our running example today, we're going to design a 4-bit counter. And its only job, literally, is to just count from 0 to 15 on every single clock pulse. We know what we want. The question is, how do we actually build it?
Well, that brings us to step 2, which is RTL design. That stands for Register Transfer Level. Using hardware description languages, like Verilog or VHDL, engineers use specialized software IDEs to write the code that dictates the chip's functional behavior. We're essentially taking our human intent for that counter and translating it into specialized code a computer can easily simulate. Step 3 is functional verification. Because, let's be real, we don't just write some RTL and cross our fingers, right? We use these super powerful software simulators, think ModelSim or Synopsys VCS, and we run test benches to prove our code perfectly mimics that exact behavior we specified. Does it actually increment from 0 to 15 and reset back to 0? If it fails the software simulation, we rewrite. Once it passes, boom, we're ready to move on.
Moving right along into Phase 2, synthesis and floor planning, where our abstract code really starts taking a physical shape.
So chronologically, we're about 2 to 3 weeks into our project now. Logic synthesis usually hits around day 15 to generate our standard cells netlist, and then by day 20, we're moving right into floor planning.
And this brilliantly illustrates step 4, logic synthesis. It is this massive leap from software into actual hardware. We use synthesis tools like Synopsys Design Compiler to completely convert our RTL code into a gate-level netlist. The software literally transforms our counter code into a network of physical building blocks. These are your standard cells, like AND gates, OR gates, and flip-flops. So the code, it's gone. We have an actual hardware schematic now.
Which leads into step 5, floor planning. Honestly, think of this exactly like an architect drawing up a master city map. We're figuring out where everything is going to live on the physical silicon chip. We're specifically allocating space for our counter's major logic blocks, routing out the power rails to ensure it gets electricity, and carefully placing the I/O pins so the chip can actually talk to the outside world.
Heading into Phase 3 now, placement, clocks, and routing. This is where physical positioning, perfect timing, and all that intricate wiring comes into play. Looking back at our roadmap, around day 21, we tackle placement. By day 25, we're executing clock tree synthesis. And hitting the 1-month mark, around day 30, we dive into routing.
Breaking that down, step 6 is placement. Using physical design software, stuff like Cadence and Nuvis or Synopsys IC Compiler, we optimally position all those standard cells right onto our floor plan. Then comes step 7, clock tree synthesis, or CTS. Remember, our 4-bit counter totally relies on clock pulses to know exactly when to count. CTS distributes that clock signal evenly to every single flip-flop with minimal skew. We're talking ensuring every single component gets that signal at the exact same fraction of a picosecond. Absolutely crucial.
Step 8 is routing. So think of this as building the highway system for our microchip city. The advanced routing algorithms inside our physical design tools take microscopic metal wires and create the physical connections between all those placed flip-flops and logic gates. Because without routing, those cells are just isolated islands, right? But wired together, they finally form our complete, communicative 4-bit counter.
And that brings us to our final phase, final checks and tape-out.
This is all about the absolute necessity of rigorous checking before we ever send this thing to the factory.
In this final stretch of the project, Day 31 is all about physical verification. Day 35 is timing sign-off. And then around Day 40, we cross the finish line with tape-out.
So, Step 9, physical verification. This relies heavily on two really critical checks, usually run through industry-standard tools like Siemens Caliber. First up is the DRC, or Design Rule Check. This makes sure our layout perfectly follows the foundry's super strict manufacturing rules, things like wire thickness and spacing. Second is LVS, Layout versus Schematic. This guarantees that the physical layout we just wired up matches our original circuit design exactly. No crossed wires, literally.
Step 10 is timing sign-off. So the crucial point is, our chip might have passed the structural checks, but is it actually fast enough? Using static timing analysis software like Synopsys PrimeTime, we verify the counter works correctly at our target frequency. If we design this counter to run at, say, 500 MHz, STA mathematically proves that the signals can actually travel through those microscopic metal wires fast enough to hit that speed safely without failing.
And finally, Step 11, tape-out. This is basically celebration day for design engineers. Tape-out is where we take our fully verified, flawlessly timed counter design and generate the massive final manufacturing file, traditionally called the GDSI file. We send that file off to the semiconductor foundry. Our job in the design flow is officially done, and the actual physical manufacturing of the silicon chip can finally begin.
If you remember just one thing from this entire explainer, let it be this simple one-line summary from our source material. The IC design flow takes an idea, codes it into Verilog RTL, puts it through strict verification, translates it into physical design, finalizes it in tape-out, and ultimately results in a physical silicon chip.
It really is just an incredibly precise, logical journey. I mean, we went from literally just saying, hey, I want a 4-bit counter, to drafting a blueprint for a flawlessly timed microscopic city made of logic gates and metal wires. So I'll leave you with this thought. Knowing all the insanely complex steps we just went through to build a tiny, simple counter, how many billions of these flawlessly routed standard cells do you think are powering the screen you're looking at right now? Wild, right? Thank you so much for joining me on this explainer. Keep learning, and I'll catch you on the next one.